Thank you, Professor. Right. Okay. So here I'm going to talk about a work that we had started back in the end of 2019, and we were really looking forward to IJCLR 2020. But unfortunately, COVID came, and whatever happened afterwards. But anyway, so I'll give a talk on this incorporating symbolic domain knowledge into graph neural networks. This is a joint work with my supervisor, Professor Ashwin Srinivasan, and a colleague of mine at industry, Lovekesh. Okay, so the main hypothesis that we are testing in this work is that the predictive performance of deep neural networks improves with inclusion of domain knowledge. So we have been seeing such kind of results over the years, and we wanted to see look at the particular kind of neural networks which are meant for graph structure data, such as GNNs. Okay, the problem is this, that standard deep networks, they just learn from data, but here we are adding this domain knowledge B into the learner, and we want to construct a model from data and the background knowledge. So few characteristics of this: the data D is relational, such as graphs. B is available in some symbolic form, such as some first-order logic rules. L is a class of deep networks which deal with specifically graphs, which are called GNNs, and M is the output of the learner that you get, a trained GNN model. Now, so some of these have been already seen in previous talks, but for clarity, I'll just go ahead quickly over this. So data are relational. For instance, if you look at a molecular if you look at a molecule, we could represent this as a molecular graph, where we have numbered these atoms with 1, 2, 3, 4, and so on, and there is a bond which corresponds to an edge in the graph. And this can be represented in Prolog or any other data log, for example, as atom and bond facts. So here it says that M1 is the molecule which has a carbon atom at position 1. And there is a bond between position 1 and 2, which is a double bond in the same molecule, and so on. And the domain knowledge is symbolic. It means that we have access to the facts and definitions of the following, like functional groups, which are, say, amine, alcohol, ether, ester, and so on. And we have some definitions of ring structures, such as aromatic, non-aromatic, and many other structures. Then we have some higher order relations, such as fused and connected structures. So more on these details could be found out in our paper. Coming down to the basics of GNNs, they deal with graph spaces. That means that each data instance is a graph. Here, the blue dots represent the positive instances, and the red ones represent the negative instances. This is just for visualization. We then mathematically represent graph G as a 5-tuple, where B is the set of vertices, E is a set of edges, and then the neighborhood function, then a vertex labeling function and edge labeling function. So an example of a labeled graph is this, where we are representing a benzene ring, where each node is labeled with carbon atom and each edge is labeled with the type of bonds between the atoms. And the labels are simply written as psi of EI is equal to C, and epsilon of EI is equal to 1 or 2, right? Okay, now how GNN works? Mainly, they relabel the graph iteratively. We define, not we define, but we formalize something called a relabel function, which transforms the graph space to a relabeled graph space. For instance, if you pass a graph with a graph VE, sigma, psi, and epsilon, you'll get VE, sigma, psi, dash, and epsilon. So if you look at it, we are just changing the vertex level here. We're not going to look at the edge levels at all. This is because of the fact that we are only using the kind of GNNs which deal with iteratively changing the node labels. So this function is implemented using the aggregate combine procedure, and in practice, we call them graph convolution or pooling operations. Then, since we'll be dealing with graph classification problem in this work, we'll be needing a vector representation for the whole graph. And that is done with a vectorized function called vec, which transforms the graph space into a real or a real d-dimensional real vector space. So this function is usually implemented using a readout procedure. And in our work, or traditionally people use global or hierarchical pooling for this, which essentially combines the node labels into the d-dimensional vector. And then that d-dimensional vector goes into a multi-layered perceptron or a single-layered network, depends. And then it produces the class label y. Or if it is a regression problem, it will produce the real value. Anyway, now that we are familiar with the basics of things that we are dealing with, now let us talk about the vertex enrichment. So this is a very simple idea that we thought about while looking at the way GNNs work. So here we treat each domain relations as a hyperedge, and a hyperedge is essentially a non-empty subset of the vertices, the set of vertices. Now, what we do is we infer these hyperedges in a graph as being present or absent. So present means the relations are being true for some nodes, and absent means the relations don't participate in that hyperedge. I'll show a few examples of these. And then we try to, we enrich the labelings of the vertices in the graph with this hyperedge information. Let's see how we do that. So let us consider a molecule M here. I don't really know what this molecule would be called in chemistry, pardon me for that. But the labeled molecular graph looks like this. I have not deliberately put the edge labels here because we are only dealing with the node labels. This is a relational data instance. And let us assume that we have access to the following domain relations, such as benzene ring, methyl group, alcohol group, and then connected structures or fused rings. And how do we infer this domain relation on this molecule? So as you can see, benzene ring is a hyperedge, which is a subset of vertices. And this is R1. Let us call this R1. And we can see that the atoms 1, 2, 3, 4, 5, 6, or the vertices 1, 2, 3, 4, 5, 6 are the member of this benzene. So this is a benzene ring. Then similarly, you get the R2, which is another benzene ring for 4, 5, 8, 9, and 10, 11. And similarly, we have this methyl group, alcohol group, then connected structures. So this is a connected structure here, and this is another connected structure here. And this is a fused ring. So these two rings are fused because they have two common atoms between them. Notice that each relation here, as inferred, is a hyperedge. And then the enrichment process is pretty simple. Basically, enriching the vertex label with the relation info, such as we know that the vertex V1 is a member of R1, vertex V2 is a member of R1 and R5, and so on. Now, if we go to the new vertex labels that we get after vertex enrichment, these are the things we get. So the V1 vertex will be labeled. It was initially, we had just the carbon here, but now since we have the hyperedge info available from here, we know that this is the benzene ring. So you can just pass this information, benzene /6. The /6 represents arity. Similarly, we have this vertex V2, which participates in this two in the benzene ring and the connected structure R5. So then we go and put these two relations in it. So similarly, for all the vertices in the molecule, we put these relation info, domain relation info based on the hyperedge that they participate in. So in the end, what we get for the whole molecule is a very simple labeled graph, which is for every node I have shown here the vertex label, new vertex label. But thing is that a GNN cannot operate when the labels are sets. So there has to be some mechanism of transforming these sets to fixed length vectors. So what we do is we transform, we have a mechanism, a simple procedure that transforms these sets, these vertex level which are sets to fixed length multi-hot vectors. So now what happens is that each vertex will now be associated with a vector, possibly a d-dimensional vector, and all the vectors will have the same length. And this has to be done for all the instances in your in the data set. Now then, a GNN can straight away operate on these graphs. So we test our model, the vertex enriched GNN. We call this whole model as the vertex enriched GNN or vegan, and we test it on 73 data sets, which are obtained from NCI, and we thank Gustav for that, for guiding us to get there. And the domain knowledge consists of hundreds of domain relations that I told earlier, such as the functional groups, rings, connected structure, fused structure, and so on. And the dataset summary are these. This is the summary of the vertex enriched graph after the enrichment has been done. So we have 73 data sets. Each of average number of instances in the graph is 3,000 roughly. Average number of atoms in molecule is 2451. Thing is that the graph doesn't change. Only thing that changes is that the labeling in the graph. So this is again same for the baseline GNN as well, which doesn't have any access to additional domain knowledge. Now, also, we do experiment on 5 different state-of-the-art variants of GNN. More of these details could be found out in our paper. Mainly, what we call variants are that the way the convolution and pooling operations are implemented. So to give few examples, we look at GCN type of convolution, then graph attention network, graph sage, and few others. So what we found out, the results are these, that we first compare our vegan results against standard baseline GNNs. So the GNN which has only access to atom and bond information. So here this table just shows out of 73 cases, in how many cases we won't win, how many cases we lose, or in how many cases the predictive accuracy is equal. So as you can see here, the vegan wins for the variant 1 in 48 cases, it loses in 14 and equal in 11. So this basically it's telling us that the results are substantial, as well can be seen as well that the p-value is quite lesser than 0.05. Further, we did another experiment where we thought that if we could incorporate some relations those are constructed by an ILP engine, which are mainly the relations which are obtained by combining the data and the background knowledge, and we can construct the higher order relations, which can be incorporated then into our vertex labeling as well. Let us call those sets as R dash, and then we try to see how many of those we add to the vertex labeling and how the GNN performs. Then we see that if we add 100 of these, with increasing number of relations, we're able to see the performance improve up to a point. Beyond this, we have not tested. But however, we are able to clearly see that there is a trend that if we increase the vertex labeling with more domain relations, the predictive performance of GNN increase across all the 5 variants that we have taken. So this shows that domain knowledge definitely helps in improving the predictive performance. This is a plot, a gain plot we call, which essentially compares how the vegan or the vegan dash. This is the standard vegan with the background knowledge. This vegan dash is with the background knowledge plus ILP constructed relations. So as you can see, do not pay attention to the ordering of this. This is just to, just to show in clear form how the differences are really. But the ordering of this plot should not be given too much importance. But as you can see clearly that adding domain relation to vertex enrichment really helps. And the way in which you are doing is a very simple idea, but still are able to get very nice results. And that is the 2 conclusions. But as you can see, let's not hope too much from this, because these results are outdated in our next work. But the limitations, as you can see, are the following. So vertex enrichment is a very simple idea, as I showed. Uh, First thing is that, as you can see, it loses the identity information of different relations, such as you can see, vertex B4 and B5, they are participant in two different benzene rings. But when you do the vertex enrichment, that identity information of the relation is lost. If we want to know in which benzene ring vertex 4 participate, we need to go and look at the graph itself or the graph structure to get that information. From vertex leveling itself, we will not be able to get that info. So there is some information loss here. Then vegan requires inputs to be graphs. Of course, it requires inputs to be graph because we're dealing with GNNs, but thing is that it limits its usage to other kind of relational data, such as if we want to deal with relational databases, for example. Vertex enrichment requires computation of all the hyperedges for the molecules given the domain relations. And this can be computationally demanding because if our background knowledge is huge and we are dealing with huge number of data instances, then this needs pre-computation of all the hyperedges information. But all of these limitations have been overcome in our next work. As I told, this pagan work itself is a very old work, at least 2 years or 1.5 years old. And we have overcome most of these limitations in our next work. Please attend that into tomorrow's talk, where we'll be really using the idea of MDIE, which is developed, which is the core of ILP, to incorporate the symbolic domain knowledge into GNNs. So the preprint is available and the work is already published in MLJ, and the codes are available in Vegan, but I would definitely redirect you to the work that we'll be showing next. Thank you. I'd like to take any question if there is.